Today, let us talk about sorting. This is the topic that links data structure with the next required course algorithm. This forms a bridge between the two topics. So, in data structure, sorting is likely to be the last topic to be discussed, and sorting is probably going to be the very first topic you will see in algorithm class. So let's start looking into this. Sorting, I believe everybody understand what this try to do. You get a sequence of numbers or whatever things that can be sorted, and usually we store those things in an array, and we try to sort from the original item into either descending or ascending order of the sequence. So let's start looking into the very basic one, insertion sort. This insertion sort can be considered as one of the most basic sorting algorithms to really sort all the things out. In this topic, in this algorithm, what I try to do is this. The list is assumed to be broken into two parts. On the left side, which is on the green colors, is the sorted segments. On the right side is the unsorted segments. This can be true even from the beginning, because if you only have one item on the left side, that is actually sorted because you only have one item. So you will start with one green item, with all of the rest items become red. And we try to start with this concept, and then we try to work on one item at a time. So what I try to do is that in this example, we look into the yellow one, which is the target one. We try to merge this item into the left part, which is the green portion. So it will try to compare one by one, and then until you find that the items before it is smaller than the yellow item, then we know it finds the right position. So we will process one item at a time and then increase one more item in the green part at a time. And therefore, we will, in this example, we will work on this one. You can see that in this case, it's actually looking into a very nice position because this one is larger than the previous one. And therefore, you can stop over there and then work on the next one. This one obviously need to travel several items until it hits very close to the beginning. And then you will process the next one and the next one. So this insertion sort is pretty basic sorting algorithm. Let's take a look of this code, because this can give us a very good understanding of what is the upper bound for the sorting algorithm. If this is a simple sorting algorithm can perform, say that it takes this amount of time, and maybe some other sorting algorithms can take much smaller amount of time compared with this one. So in this insertion sort, the code is pretty simple. And basically, this is part of your final project actually. So you see, I already provide you the code. Basically, this code can be copy and paste and almost workable for your final project. So let's take a look at this. What it's trying to do is that starting from p equals to 1, p less than size, p plus plus. So what this p trying to do is that starting with the first item, like I mentioned, the very first item is already sorted, so you don't need to start with index of 0. You will start with index of 1. And then we try to work this for loop, try to help you to identify the yellow item one by one from the index of 1 goes to 2, goes to 3, goes to 4 until the end of it. So this is what the basic loop going to be. So this forms you n items in the loop. And then after that, you try to remember what is the yellow item. So you try to create a temp variable to store that value and then define a j for your second loop. So obviously you can see that this is the loop, this is another loop. They are nested to each other. What is the next loop trying to do? Is starting j equals to p. So starting from the yellow item, you try to go backward. That's why you have a j minus minus over here. And the condition is this. As long as j is greater than 0, so it's not work all over the end of it. And the value that you are looking at, the yellow item, is still less than the j minus 1 than the previous one. So starting with this one is this, if this is smaller than that one and j is still greater than 0, then we need to keep moving for your loop. So in this case, every time we move, we basically need to swap the two values so that this taller one will stays in the current yellow one, and this yellow one will be in here. Keep moving, try to compare with the previous one. If they move, they will swap the value until either of the case is there, and then we will stop the loop and basically make sure that you put the yellow item into that location, which is the correct position. And therefore, you can see that when we're trying to do this one for the same code, originally this is the sequence that we have. Like I mentioned, when p is equal to 1, if we try to trace the code from the beginning, p equals to 1, which is indicating in here, this is identified as the yellow item, the left side is the green item, and the rest part of it is unsorted portion. So what it's trying to do is that we try to create a temp equals to a of p, which temp right now equal to 94. So j, int j for j equals to p, then what we are going to do is that we say it is value of 1, and this is not a true case because temp, which is 94, is not less than a of j minus 1, which is 81, and therefore we don't need to do anything. Basically, this is finding the right position for the yellow items that we have. And therefore, the loop will go back and come back over here, and we will try to move p to the next location. So now when p equals to 11, we try to store the value of 11. Now j equals to p, which is 2. We need to test whether or not this is a true statement. J is greater than 0, that's true, and temp is less than j minus 1, which is 94, and that's also true. So what we need to do is that we need to swap the two values. So you can see aj, which is index of 2, equals to aj minus 1. So 94 will still stays in here. 11 will comes ideally in here, but you still need to test whether or not you need to swap. In this case, it's also a true statement because at this time, j is equals to 1 and j is greater than 0, and temp is less than a of j minus 1, which is 81 is greater than 11, which 11 is less than 81, and therefore we need to swap the two values. So we need to put 81 over here, and then we will come back to the j, and this time come back to the j loop, and then this time j will equals to 0, and therefore we don't satisfy this condition over here. Let's know it's already hit the beginning of the array, and therefore we don't need to do anything. At this time, we put temp into j, a of j, which is 0, and therefore you can see that we will end up with the sequence like this. Of course, p will keep moving forward to the next location. At this time, you can see that 96 is actually is at its own spot, and therefore we'll still do the operation over here. Temp equals to 96. Immediately, this condition is not going to satisfy, and therefore we don't need to move the loop at all. aj equals to temp, so we put 96 on 96 again. So we will move to the next one. When p equals to 4, we will see that we try to use the temp equal to 12, and then we will keep moving. So basically you can see that this 12 will swap here, swap here, swap here, and then basically finding out this is not less than 11, and therefore you can stays over there, end up with the sequence like this. And therefore, this is what's happening. Of course, the first loop will keep moving from this location to this location to this location until the end of it. That's when the first loop finished. And therefore, you can see that if you analyze this algorithm, you see this is an n-loop operation. And in here, it's smaller than n, but basically when I move to the rightmost locations, you have more items that possibly need to travel to. So this is proportion to the n operation, and therefore, since this p loop and this j loop are nested with each other, this algorithm is going to give you an n squared operation. So the worst case scenario for the insertion sort is that if the items are reversed sorted, That means every time you try to process one item, the yellow item need to go all the way to the beginning. And then the operating of the swapping is actually cost you a lot of time. However, this gives you an upper bound of the sorting algorithm. To me, another similar concept of this sorting algorithm would be starting with the whole sequence. You try to find a minimum and then swap that minimum items to the very first location, and now you have a space with n-1 space to search for. So you are starting with the first the index of y, which is the second location, until the end of it. Try to find the minimum in this range and then swap to the second location, and we can also keep doing that. It's giving you a very similar operation. So basically these are like the most basic sorting algorithms to sort a sequence. To discover an optimal algorithm, we need to find an upper and lower bound for the problem. And an algorithm gives us an upper bound, so basically this is what we get. The worst case scenario is basically n squared. This tells you that if you are writing or developing a sorting algorithm, then that's worse than n squared, something is wrong over there. There's no need to go more complicated or more slower than what we have seen in this insertion sort operation. However, upper bound is easier to bound. For the lower bound, it's probably not that straightforward. And therefore, what we want to discuss in this chapter or this topic is that how do we find some algorithms that actually gives better performances than the insertion sort. So the only operation used for sorting in what we have discussed is swapping the two keys. And you know, swapping the two keys is actually very time consuming because this operation is going to cost you big of n already. Every time you swap, shift, these kind of things, they are not an ideal way of doing so. This kind of sorting algorithm is pretty normal. You see the insertion sort, you see what we discussed about the finding the minimum and then do that one by one. Or we also see something like bubble sort. All of these will have some properties that swap one item at a time. So the next interesting sorting algorithm I want to talk about, which is the idea of the shell sort, is that saying we have some methods to swap. Instead of one by one swap with your neighbor, you swap with a much bigger distances. And by doing so, you can basically having the random sample, that kind of concept, try to find a pool of it, swap the two items that are very far away, and ideally this kind of swap saves you a lot of smaller swapping by the neighbor's time, and therefore it can better give you a better or a closer to an optimal solution for the insertion sort. This sounds interesting, so let's take a look of this. How is this going to happen? So take a look of this one, saying that here is the array that for us to be sorted. So we have quite a few items. Instead of sorting one item and swap two items to the neighbor, let's use a concept of the random sample. So saying that for the first one, I want to look into the fifth one, ninth one, and the next every 5 items. I'm interested in those. So these are the red items that I have colored out. And what we are trying to do is this. There are 5 items in the red color. We pull those things out, sort those 5 items, and then put them back to their corresponding position. So which means that the smallest item of the red item we will put in here. The next smallest one is put in here. The middle one will put in here. The largest one is the one that we put in this red box. So you can see that by doing so, we have the capability of pull out the sample size, sort it, and then they will be able to jump into different locations. And ideally, because this is the random sample concept, the smallest one of the red one is probably the smaller items in the whole sequence. So using this idea, we will move on to the next location, which is the yellow items. We do the same thing. We will do the green item, we will do the blue item, we will do the purple item. So when we doing this, obviously, after this operation, we are not going to get a sorted sequence because these are random samples. However, after this operation, the sequence that we have is closer to an optimal situation for the insertion sort. And of course, in the end of this sequence series of operations, we will still need to perform an insertion sort to get a finally sorted segments. However, this insertion sort is very close to an optimal solution. Let's take a look at a real example and see what's really happening. So what we're going to see over here, the red one, because the gap is 5, then we call that as a 5 sort, a gap 5 of sorting. After that, we can do a smaller gap size, but in the end, we still need to perform an insertion sort, which is a gap size of 1. That's the neighbors with each other. And let's see what's happening. Saying that this is the sequence that we want to do the shell sort about. So as we mentioned, we're starting doing a 5 sort, a gap size of 5. So I colored out 81, 35, and 41 as the red color. And then we try to pull all those 3 numbers out, sort it, and then put them back according to the order. And then I pull out the next one, which are the yellow items, put in all those three items out, sort it, put it back. So you can see after just these 2 operations, 17 and 35 are like smaller. Of course, 35 is not really a smaller among all the sequence that we have. However, I want you guys to see 91 or 94 over here. Originally, it's the second item. After this operation, it has been shifted to close to the end of the sequence. And you probably notice 94, 95, 96, those are the 3 largest numbers of the sequence. So by doing so, we will be able to move the items away and make it closer to where it's supposed to be. And of course, we will do the green one, which end up with this, the blue one, the yellow, purple one. So we will have a 5 sort sequence over here. This is closer to a sorted segments than the original one. But of course, this is not sorted. It's totally possible to perform a one more layer of the gap sorting, which would say 3 sort. So for that 3 sort, we will work on the 5 sort result. There's no reason that you go back to the original. After you do a 5 sort, you go back to the original, do a 3 sort, right? You would use the 3 sort on the result of the 5 sort. So you minimize the gap size, hopefully to give you even more closer to the optimal solution. And therefore, you see that we do the same thing, pull out the 3 sorts, and with the gap size of the 3, all of these 5 items are in the red color. We pull out those 5 items, sort it, and put 28, 35, 58, 75, and 95. And we would be able to do that for the yellow item, for the green item, and you can see that this sequence is much, much better than the original one. And finally, we still perform a 1 sort, which is an insertion sort on the result of the 3 sort and give us the sorted segments. Okay, it sounds a little bit much more, it sounds very complicated actually, much more complicated than the original insertion sort. But let's take a look of the analysis of it. For a large array, we don't want to do a 5 sort in the beginning. Say now you have 1 million items. It's probably not a good idea to do a 5 sort. So we need to do some number of the sort. But how do we find the number? Okay, this is actually a very interesting topic in the shell sort. So say now I have 1,000 items. We have some numbers given here. 364, 120, 140, 13, 4, and 1 sort. So you may have the question, why we have generating those numbers? And that is actually a very interesting topic. There are many, many different ways of generating those gap size. So here is one example. Say now h equals to 1. So that's the first one. We will need to do the 1 sort. Basically, this is the bottom. And then the next value would be 3 multiply h plus 1. Obviously, the next value is 4. The next value is 4 multiplies 3 plus 1 give you 13. 13 multiplies 3 plus 1 equals to 40. So this number obviously similar to the Fibonacci numbers. It can keep growing bigger and bigger, and depending on what is the input data size that you have, you will use those numbers to help you decide your gap size. For example, you have 1,000 items. 1,000 items, there's no reason you do 1093, right? So you will use a 364 sort out basically 3 items at a time. Some of them are 3, some of them are 2, and then use 121, 40, 13, 4, and 1. So this is one good way of doing the sure sort and help you deciding the gap size. Another way of doing that is similar to this one. Hi equals to floor of hi minus 1 divided by 2.2. So depending on your size of n, you divided those things by 2.2, get a value of the floor of that value, and then use that value to divide 2.2 again to decrease the gap size. So basically this is also another way of doing so. What is the real running time of the sure sort? Nobody knows. This is like a mysterious sorting algorithm. However, we know it is running better. It's running better than the insertion sort because it provides a better condition when you finally feed the things into the insertion sort. The real analysis of this one is not as easy as other sorting algorithms. So there's not really a mathematical proof indicating what is the big analysis of this one, but we sometimes just, for computer science, you just run a program with a large amount of data, do several experiments, and then try to get the estimation of what is the performance.